Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. In the last week we have seen how material properties of various materials or optical properties of various materials can be modeled. We looked at the Lorentz model, Drude-Lorentz model and so on. So this way we will talk about one of the fascinating aspects of nanophotonics, that is plasmonics. So I think in the introductory video I showed you this slide wherein I mentioned about the Lycurgus cup, which is a Roman artifact back from 4th century, which exhibits different colors depending on where the optical illumination is. For example, if you look at it in reflection, it looks greenish, whereas if you look at it in transmission, that means you put a light inside the cup and then look at it in a transmission mode, you see that it is reddish. And we also mentioned these stained glass windows that are seen all across Europe in the churches. So, and we briefly mentioned that the colors are not because of any dye, but because of presence of small amounts of noble metal nanoparticles. So while making the glass, they used to mix a tiny amount of gold and silver that would form a colloid, and then that will actually cause this structural color. So in this week, we will try to understand some of these things based on fundamental ideas of plasmonics. Okay, what is a plasmon? Okay, why is it a different name? A plasmon is essentially a quasi-particle, or rather a collective excitation that occurs when a photon interacts with electrons in a material. So basically a plasmon can be thought of as a photon coupled to a electron. Okay, so when you have such a coupling happening, we refer to as plasmon. Okay, and we will go deeper into this as we go along. But before I go into the specifics of how light interacts with metal nanoparticles, I want to briefly touch upon the phenomena of scattering. Scattering is a very commonplace thing that we see all across our lives. And the way to think about it is this. So let's think of a light beam which is incident on a particle. Okay, it could be a nanoparticle or it could be a micron scale particle as well. So what happens? Let's say now I have this light of let's say various colors are present on that, and that is incident on a particle. What would you expect? Well, we already understand this when we discussed about the material properties, right? So essentially the material is consisting of, if it's a dielectric, it consists of, let's say bound electrons which move in response to the electric field. In a metal you have the free electrons, right? So now if I introduce a particle like this, how do I understand its behavior? Well, this follows the familiar Lorentz model that we have already seen. So we have seen this example of a spring mass system, wherein we can think of an electron as bound to a nucleus through a spring constant. And we said, okay, there is a characteristic resonance frequency, and then because of that you can describe the response of the electrons, right? The same phenomena is applicable here. Let's say if I have a nanoparticle or a micron size particle, when light is incident on that, it will cause some polarization. Okay, and we can actually capture that polarization in terms of the Lorentz model. So without actually going through all the details, I am just writing the expression for the dipole moment in terms of the electric field. So here EL is my electric field, right? Incident light or electric field. Okay, and now in response to that there is a dipole moment which is created, which I am referring to as P. All right, so that dipole moment has this term. If you look back in the basic electrodynamics, you will see that the dipole moment is nothing but polarizability alpha times electric field. Okay, so this coefficient that you are seeing here we refer to as atomic polarizability, which is given by the Lorentz model. So it has this characteristic resonance frequency and negative frequency squared, and then negative of I gamma omega. So this is a resonant behavior, right? So now what you think will happen when I am close to the resonant frequency? Okay, we understand that when we are close to the resonant frequency, this denominator will become very small, that means it's going to blow up. The dipole moment is going to become large. So what? A dipole moment essentially means you have this incident light which is causing this dipole to be created, and the dipole is oscillating in time. So it essentially creates secondary radiation that we will refer to as scattered intensity. Okay. So essentially, if I think of a nanoparticle here and light is incident on that nanoparticle, in addition to the, some of the light will get transmitted. Maybe I can show it as, smaller intensity of light which is getting transmitted. But in addition, the light will be scattered in various directions. Okay, that is shown by this, illustrated by these arrows. So light is getting scattered in various directions. And this is a very familiar concept. When we look at dipole antenna, we take the dipole moment, right? And then we look at how the scattered intensity looks like. We studied this in basic antennas and electrodynamics. So we'll see that if I have such a dipole which is created by light, the only difference is the dipole is now oscillating at the frequency of light. That's the only difference. Okay. When you have such a dipole, my scattered intensity will exhibit a donut shape pattern that we have already seen, in our basic courses. So essentially, along the direction of the dipole, there is no emission, but in the perpendicular plane, isotropically it emits, and that's why this donut shape. So this is a scattering phenomena that is very common. We see right from nanoscale particles to micron scale particles to even larger objects. We see scattering. That's a very common phenomena. Okay. So as I mentioned, we know how the scattered intensity for a dipole antenna looks like. So where, this is the dipole moment and you have the characteristic fourth power of frequency, and there is also sine square dependence, saying that along the direction of the dipole, there is no emission. So now in place of the dipole moment, I'll put in my Lorentz model for the dipole moment that I got. So essentially this Lorentz oscillator term. When I substitute, I see that my scattered intensity is again going to exhibit the familiar Lorentz form, wherein this particular term here is capturing the resonant response. Resonant response of the particle. Okay. And what are the conclusions when we see a resonant response? Well, the scattered intensity is going to be strongest at the resonance frequency, right? When my omega is close to omega naught, right? That is where I get the strongest scattering intensity. If I go away from it or I detune from the resonant frequency, then I will not see significant scattering. All right. And we also see that the scattering is dependent on wavelength. It is not independent of, it is quite dependent on wavelength, basically in terms of lambda to the power of 4. For example, if I take an intensity which is, let me say, I'll take a 800 nanometer light. Okay. I'll take 800 nanometer light and I compare the scattered intensity with, let's say, 400 nanometer light. So essentially I'm making the wavelength half. When I do that, I'll immediately see from the expression that the scattered intensity for 400 nanometers is going to be stronger by 2 power 4, right? So it's 16 times stronger. 16 times stronger scattered intensity. So it depends very strongly on the wavelength. Okay. And also you see that there is a sine square dependence. That means that in the forward, if I think of a dipole which is in the z direction, in the forward and the backward direction, there's equal amount of scattering. Okay. There is no preferential direction, in fact. Okay. All over the azimuthal plane, you will see that there is scattered intensity. Okay. So these are the common phenomena that you see for scattered light. Okay. Why do we think that is important? Well, this basic concept, which you have already understood in some way before, it explains a lot of interesting things that we look at, see. For example, why is the sky blue? That's a question that you might have asked. Okay. Well, the sky is blue because you have the incident electromagnetic energy from the sun, and then the atmosphere has a lot of these molecules. For example, let's say maybe, N2, nitrogen molecules, or let's say, or oxygen molecules. So all of these are basically less than 1 nanometer size objects, right? There is this bond length which will be roughly about 0.3 nanometers, and there are two of these bonds there is a bond in O2, right? So definitely less than nanometer, and nitrogen as well. So the bond lengths are all well known in chemistry. So when light interacts with that, clearly because the size is very small, the omega naught for these molecules is going to be much, much larger than the typical frequencies associated with light. Okay. If, for example, visible light is what we can see, and the omega naught for these bonds, because of the small size, it's going to be very strong, very large. And essentially what you'll end up getting is your scattered intensity is going to be a non-resonant phenomena. Okay. So it's just that, omega square doesn't matter because omega naught is very, very large. So compared to omega, so the denominator essentially becomes omega naught square. Okay. And so it's a non-resonant phenomena. That means it's not exactly a particular wavelength you see a very strong color and then nothing else. Not like that. It's broadband response. Okay. And now what happens when you compare, let's say 700 nanometers, that is the red light or deep red light, and let's say 400 nanometers, which is bluish. If I compare these two, I'll immediately see that this 400 blue is scattered strongly. So that means that my incoming light is incident in the atmosphere and it's getting scattered in all directions, and blue is getting scattered better. For example, if the sun is at an angle, most of the red light is going through, but only the scattered blue light is reaching your eyes. That's why the sky looks blue. And if you have looked at any pictures of, let's say, Earth taken from a spacecraft, you would typically see that, there is this bluish thing and then outside it's all black, because there's no atmosphere, there is no scattering, there is no light from there. Okay. Only from Earth, where you have a lot of this atmosphere, you see the blue color. All right. And this also explains why, for example, if you look at dawn or dusk, the sun looks reddish, right? It's all, the horizon is reddish at dawn and dusk, or orange-ish color. Why does that happen? Well, it happens because now when the sun is at the horizon, the distance traveled by light before it reaches your eyes is longer, and all across that distance, the blue light is getting scattered in all directions, and only the remaining red light, which is the scattered minimum amount, is actually reaching you. That's why it looks reddish. Okay. And you just look at the world around you, and it's very simple phenomena that we see. Okay. For example, the clouds as well. The clouds are white because there is a distribution of particle sizes, and they're kind of large compared, they are not very small particles compared to they're water droplets essentially in clouds. And they are much larger than the wavelength, or typically of the same order, and they scatter all the wavelengths equally, and that's why they look whitish. Okay. So you see that this simple idea of scattering is very important, okay, in understanding, and we call this as Rayleigh scattering. Whenever the size of the particle is smaller than the wavelength, we call this Rayleigh scattering. And we also have Mie scattering, which deals with the slightly larger particles. And then of course in the large scale objects, you have the regular planar optics. Okay. So with this introduction of scattering, I'll stop this particular short video, and then in the next video, I'll talk about what happens when light hits a plasmonic particle or a metal nanostructure. All right. I'll see you then. Thank you so much.